Okay, I'd like to start with something fun with you guys. Reading week is coming up. I have no assignments for you, but I do have a little challenge for you to try. What I will do is I will show you some program here, and you can definitely watch the recording later to see how you can implement a program. But let's demonstrate that to you. It's more like a magic. Anyone want to volunteer? Just one person. Maybe someone from the back, if you haven't really participated in the class. Just one person. Anyone. You want to try? Okay, sure, okay. What I will do is I will show you this particular program here on Eclipse. Okay, we can try it together. Basically, what I will do is I will launch the program here on Eclipse. Your name? Wilson? Like that? Okay. Now, have a look at this particular input over here. So this is how it's going to work. Wilson, I want you to choose a card from these, it's about 21 cards over here. Choose one of them and tell the rest of the class which one you chose. But meanwhile, I'm going to walk out of the room. Don't tell me. Okay? You know what you can do? What you can do is, come over here. What you should do is write it up over here, exactly which card you chose. After that, erase it. So once everybody knows which one you choose, don't tell me, right?
Okay.
I'm going to walk out of the classroom for 20 seconds. Do it quick. Yeah, thank you. All right. Well, you can see that basically I didn't change anything, right? The program was already started. There's no way for the program to know which card he chose. Everybody knows, right? So now, basically, Wilson, so I'm going to ask you 3 questions, right? No, nothing to do with prime number. Let's enjoy the game. It's a magic, right? So Wilson, let's make some convention here. This is vertical one is column number 1. This is column number 2. This is column number 3, okay? 1, 2, and 3. Okay, let's start. Question number 1, which column, don't tell me which column and row, which column does your card locate? Column 3, okay. Everybody agree? Okay, column 3, and then as soon as I hit enter, the cards will be reshuffled. Now, second question, tell me which column it is. Column 2, okay, everybody agree? Okay. Column 2, okay. Last question, which column? Column 2? You're pretty sure, right? Okay. Because if you didn't tell me the truth, it's not going to work. Okay, 3 questions. Now, the program, or me, who programmed the program, knows which card you chose. Okay, let's see. Is that a 1? Guys, it's magic. All right? Okay, now, let me tell you the truth. Nothing is magic here. It's based on pure math. Okay? Here's my challenge to you. If you are interested in taking this challenge, guess what? You can use 3-dimensional array to practice this particular problem. I will leave it completely optional to you. If you want to do some programming exercise during the reading week, do it and show it to me later. I'll give you some comments. Okay? Not for credits, just for your personal satisfaction. Now, I want to show you just one website. Okay, so when you rewatch the video, you can definitely go to that link. So this is a website for kids tricks. It's one of them. Okay, so I would suggest go to the website there. They kind of tell you exactly how the magic is going to be manipulated. It doesn't really tell you the mathematical reasoning. If you're interested in knowing, drop by my office hour, I will tell you. Okay, but this will be enough information for you to program whatever I just show you. Give it a try, and then if you want to show it to me, I'll be happy to see it. For myself, I use about, including everything, about 120 lines of code. Try to, well, I'm sure you can do better than I did. If you can do it better, I'll be happy to be impressed. Okay, that's about something for you in the reading week if you're bored? All right.
Are we forced to have like 21 cars, or can we add more or less?
So basically, you're choosing 21 cards randomly from the different, I forgot, in poker you got 51, right? Yeah, you got 51 or whatever number it is, right? You get, basically choose 21 out of 54 or 51 randomly. But anyway, you got the problem description here. If you want to know more, just rewatch the video.
Can you post it?
I can post it, yes. Okay, I'll make it on the Moodle announcement again. All right? All right. You know what? Let's see who actually finished that first for the class. If that person finished soon enough, maybe I should give a little prize, right? Okay, again, it's not for any extra credits. It's only for satisfying yourself. Okay? Then it's up to you. It's optional. All right? Okay, let's go back to hash table. All right. Now, today I would like to definitely finish the hash table topics here, and then I would like to touch upon a little bit about asymptotic analysis. That one is more about math. Any one of you took 1019 already? Any one of you? Okay, not many. That's okay. That's okay. So I'm going to assume nobody took it. Okay, but if you have taken that, maybe there might be some new insight. Okay, now I would like to go back to hash table. Let me just remind you, why are we doing this? Let's get a big picture very clear. We talked about the concept for map last time. So you got a collection of entries. Each entry has a key and a value. Key is used for search purpose. And the naive implementation we got is simply use a one-dimensional array over here and simply insert the entries in order one by one. That's how we did it. And we criticized about it last time. The problem is the number of iterations you have to run through in the worst case might just be the same as the size of the collection. In this case, it can be 1 million, can be 2 million, can be even larger. That's the problem for this naive implementation. That's why we moved to something called hashing. Okay, I'm going to start from scratch again, also as a recap. So everybody will be, I see no knowledge from last time for the hashing part. So this is what we're going to do. First of all, let's have a look at, we got each entry will be a key and a value. Okay, so for example, we got key number 1, and also the associated value will be D. So before we try to insert into this particular array, so the hashing idea is also for one-dimensional array, but the way you store entries into the array is completely different. It's going to be much more efficient. There is no iteration required. Okay, let's assume that we have an array called A, and the size is simply just 10. Size is 11. Okay. Let's see exactly how we do it. Okay, and we follow the process there, and then I will tell you why. I'll give you some intuition why it is efficient. This is what we should do. The idea is every time when you are given a key, I'll say K over here. In this case, key can be 1, can be 25, can be 3, 14, 6, 39, and 7. Can be any key. The idea is we're going to somehow turn this key into some value I, somehow. That's the process called hashing. Okay, I'll write it down here, hashing. And this I over here is guaranteed to be a valid index for this particular array that we're considering, which means I should be in the range between 0 and 10. So we are not using K directly. We're using the I that was converted from K. Okay? So now the hashing process over here relies on something called hash function. Okay, I'll just say hash code. So HC over here means hash code. So now, every time as far as this course is concerned, you will always be given how this hashing should be done. You will always be given the formula. So I'll give you the formula right away. And let's see how we can apply that. HC applied to K over here. In this case, I would simply say whatever the K value is, modulo the size of A, 11. Okay, just 11 over here. Okay, so that's the formula, you just take it for granted. But let's see what's the consequence of applying this formula over here. Okay, I'm going to switch the color here. Let me use green for the hash value. Okay, so now 1 modulo 11 will be 1. 25 modulo 11 will be 3. Okay, I'll just keep repeating, but if I got something wrong, remind me. 3 modulo 11 will also be 3, and 14 modulo 11 will also be 3. 6 modulo 11 will be 6, 39 modulo 11 will be 6, and 7 modulo 11 will be 7. Okay? So far, so good. Of course, you can observe that we do have some hash code over here being the same for different keys. That's observation number 1. It's something called collision, okay? I will deal with that just a little bit later. Let's see exactly how we can use the value of hash code over here. As I said before, these will be guaranteed to be valid indices of the array A. As you can see, every one of them is a valid index, right? On the other hand, 25 over here is not a valid index, right? So now how do we store the entries into the array? This is how we do it. First of all, we look at let's say I want to store this particular entry into the map or the hash table. This is how I do it. I know that 1 as the key value has the corresponding hash code 1. So what I would do is I will go to index 1 over here, and then I will put this particular entry there. So you can see I will just conceptually, I'm going to get 1 and also D as the first entry store. Let's see the second one. What about 25 and C? In this case, you can see the key value is completely different from the hash code, right? And we are using the hash code as the index. So that means we'll go to index number 3 over here, and then we're going to store the following record, 25 and C. So we'll put 25 and C over here. So far so good? One thing to note, the way you store the entry into the array is by looking at what the hash code is, so you know which index to go into. But when you store the actual entry, you gotta put 25, the original key, okay? Now here comes the question. For the next one, if I got 3 and F, apparently you can see the hash code is 3, which was duplicated from the previous one. How do we deal with this kind of collision case? Conceptually, it's easy. Just put them together in the same spot, conceptually, okay? So now in this case, that means we still go to index 3 over here, and then we're gonna store 3 and F. So I'll put 3 and F over here. That's how we store it, okay? I'll get to this particular scenario in just a moment, okay? Now let's complete the rest. What about 14 and Z? Well, the same spot, agree? Because the index value for hash code is 3. So I will store 14 and Z over here. And then I'll do the next one, 6 and A. So that'll be a different index, right? That'll be index 6. So under index 6, I'm going to put 6 and A. Okay, after that, I got 39 and C. Again, it's the same hash code, which is 6. So I'll put it just under that. So it's going to be 39 and A. Okay, final one, we got 7 and Q. So that means I'm going to get hash code 7. So I'm going to get 7 and Q. So far, so good? Yes, question? 39, thank you. Thank you so much. Appreciate that. For 39, that should be C. Thank you. Okay, so far so good. Let me just draw you one more attention to the stuff over here. Have a look at for particular 3 over here. The reason that these 3 entries are stored under index 3 was because these 3 keys over here, 25, 3, and 14, they have the same hash code, which is 3. That's the reason. Similarly, 6 and 39, the keys are different, but they actually got the same hash code, which is 6. That's why they're stored under this. Okay? Let me show you one more picture before I talk about the performance. Okay? So now this is conceptually how you can view the same map over here, right? The one I drew over here and the one over here. This is something called bucket array. So the way you can think of it is each index over here, rather than storing a single entry, is storing a bucket of entries over here. A bucket can contain multiple entries if they have the same hash code, collision. Okay? Okay, so far so good. Now the question is, in the previous implementation, the bottleneck is really about doing the search, right? The way you do the search, you gotta do a for loop and going from index 0. In the worst case, it might go all the way to the end of the array. That's in the naive implementation. But now over here, how do I do a search? For example, if I try the following, let's say I have a map called M implemented exactly this way by doing hashing. If I say get the corresponding entry or value for key, let's say 7. Let's say this. So what would be the procedure involved in order for me to search it, to find it? Do I need a loop anymore? The answer is no, simply because we assume the way you store the associated entry for this particular key value, the way you store it, is by first of all converting 7 into its hash code. In this case, just simply 7. Right? So I can simply go to index 7, and then I can just find it. Okay? Let's see a slightly different case. What about when I say m.get, and then let's say 14. In this case, apparently I cannot use just 14 directly as indices because 14 is not a valid index in this array. It's simply not. So the way I do it is very easy. First of all, I will say what's the hash code for key 14. So 14 modulo 11 will be exactly 3. So I know that when I store this particular entry, it must have been stored in index 3. So I go to index 3 here, but unfortunately, I got actually a bucket over here of 3 entries. So what I should do, unavoidably, is to look through the bucket one by one to see which entry has exactly the same key as 14. In this case, it is this entry. So unavoidably, if you do have collision, like a bucket in this, for example, 25, 3, and 14, they all have the same hash code. You have to run a loop to say, go over every entry in the bucket, and then to see which one has the key that is equal to the one I'm searching for. It's unavoidable. Let me just say one more thing before I take your question. So now this is something that's beyond the scope of this course. When you are given a hash function, we assume it is good. But what does it really mean to be good? Here's one criterion. The bucket size statistically cannot be too large. If you simply got a bucket size, that's simply just 1 million. That's useless, right? But however, if you can somehow work on your hash function such that each bucket size is quite balanced out, is quite uniformly distributed, then you actually don't take too much search time within the bucket. But that's up to 2011. Okay, I'll just tell you the concept. It's also on the slides. Questions?
Number 11 comes from the length of the array, right?
Correct. Yeah, so let me just mention one more thing. So, yes. The formula over here is a very common strategy for doing the hash function. Basically, based on how much spaces you have in the array. In this case, you got an array of size 11. Typically, the size of the array should be a prime number, typically. Okay, that's a kind of strategy, right? Yeah. So once you get to modulo the size of the array, you're guaranteed to get a valid index when you compute a hash code.
Second question is that with the bucket, can we use another hash code again?
Okay, the question is, within the bucket, can you just try to use another hash code? I would say it's possible. Let's not get there. Because for this course, we just want to understand it's a bucket. Somehow you got to search through the buckets. And one more thing to mention, which will be related to the Java code we're going to go through. Remember this. Let's say 25, 3, and 14. So they are different keys, right? 25 is different from 3. 3 is different from 14. But they happen to get the same hash code. So what we got to make sure is, when we go to this particular bucket over here, the way we can find out the right entry is by comparing the key value over here. Okay, that's a key thing too. I'll remind you again when we see the sample code. Okay, let's now talk about performance. The way we do the search now, there are 2 steps basically. I already put it there. Let's go over that. And let's see why they are really efficient. If you look at that, step number 1, we have given some key, simply k. We have to first of all calculate what's the hash code for that particular key. Once we know the hash code, that will simply correspond to the index somewhere in the array, right? The calculation of a modular operation in this case is incredibly cheap. Okay? It's more like a primitive operation, so you wouldn't take any loop to calculate. It's something that can be done very efficiently, now as opposed to running a for loop. On the other hand, see the second step over here. Once we get a hash code, which is guaranteed to be a valid index into the array, we can simply use that value there as a index into the array, right? So we can simply go to the array A and for that particular index, right? Let me just apply one more example to show you. let's say I'm trying to search for key 25, let's say 25. First of all, what's the hash code for 25? 25 modulo 11 will be 3. Okay, that's a hash code. So that means we don't use 25 over here, we simply use the hash code 3. And then go to index 3, and then we get to the bucket, and then we search through one by one if there's any collision. Okay, any question about this so far? Yes?
So our hash maps
Yeah.
typically done using two-dimensional arrays like you're showing, or are they done using an array list or something?
Okay, you mean just for hash, how you implement hash map, right?
Yeah.
Okay, good.
Or, sorry, like, so how you implement
The bucket. Yes, good question, good. Sure. So Jordan's question was, how would you implement this exactly? Okay, I'll just briefly mention that. I would say, first of all, for this first level over here, just for this particular array, that one, which is a one-dimensional array, because you can get indexing quite easily. But how you implement this bucket over here, I would say that's something you have to decide. You can either use just an array list, or in 2011, you got to learn something about binary search tree. That can also be very useful. But anyway, I'm just saying, for as far as this course is concerned, just think of them as a bucket. If you really want to try to implement by yourself, just use a single one-dimensional array. That can also work. Okay? Hey, guys, any question about what I have said so far? As long as you get the concept sorted, hopefully the code will be quite straightforward to go through. Okay? Okay, once we're done with this, there's a bucket array. Okay, one more thing to show you again. The way on the slides, the way you read through the bucket array is you can see 25, 3, and 14. So they are different keys, values, but they have the same hash code, 3. Okay, just emphasize again. And how do you search through a bucket where entry keys have the same hash code? For example, here, go through the bucket element one by one. Okay, good. So now what I would like to do is to go over some code with you and see how we can sort out several issues. Okay, just a few code fragments. You can think about the hash code over here. Let me just show you this. Let's say we have a class called integer key. Let me highlight it. Let me use a different color. That will be more effective. So we have a class called integer key, and there's only one particular integer attribute called k, just k value. Okay, which is make it an object. Oh, by the way, in general, over here for illustration, I said that k is simply an integer. But in general, it doesn't have to be. The way we just use integer to illustrate integer key, so it's easier for us to apply for the modulo. But in general, it can be any object type you like. It can be a person, it can be an account, it can be anything. Okay? So now let's see how we can do it. We have a class called integer key, and it has a single attribute called k of type integer. Okay, so we have a constructor over here, simply initialize the key value like this. For example, let me give you one example. How do you initialize a key like 25 over here? You will simply say integer key, let's say ik underscore 25. Okay, for the value, you can say new integer key, and then just pass the value of the key. As easy as that, okay? Now, look at this. Also, we got an equals method, which you are very familiar with. We'll go over that in just a moment. We also have a hash code method, like what you did in lab number 2, okay? For now, you can think about hash code is similar to equals in the following sense. We talk about, we do have some default version for the equals method, right, in the object class. We also have some default version for hash code, okay? For you to understand, which I'll give you an example for now, the default version for the hash code that you actually get from the object class simply give you some integer representing the object's address, which means as long as there are different addresses, they'll give you different hash code, okay, just based on addresses by default. But typically you want to override them, which means you have what I'm doing over here. You can see for the hash code over here, I simply return what we said before, k modulo 11. Okay, exactly the same formula, the same example. So now what about the equals method over here? For the equals method, we did what we are used to from before. Nothing is special here. But the way we compare to see if two keys are equal or not, we simply say this.k equals other.k, because k is an integer. Okay, so far so good? So now we have two methods to worry about. We have hash code, and we also have equals method. Okay? Let's see some tests very quickly before I pose a question to you. Okay, now assuming that the hash code will simply do k modulo 11. Let's see example over here. Okay? Let's now say we create an integer key ik1, and then with a key value 1. You can think about ik1 is simply pointing to some integer key object over here, and with only one attributes k in here. So k has the value of 1. Okay? And then we want to do some assert. Okay? We want to say assert ik1 the hash code. And hash code was exactly defined over here, right? It would be the k attribute value modulo 11. That's, in that case, ik1 dot k modulo 11 would be 1 modulo 11, which would be 1. Agree? So that's why we get 1 over here. Okay, let's see more examples. Let's say we got another integer key over here. Let's call it ik31 underscore 1. Okay? What I would do is I will say new integer key and then 39. How does it look like? Let me use a different color here. So basically what I'm doing here is I would say ik39 1 is pointing to some integer key object over here where the k value is simply 39. Okay, that's what that line does. What about the next line? Next line basically is creating a new object, a separate object, ik39 underscore 2 with just the same value, but it's different objects, right? So that means we got ik39 underscore 2. It's pointing to some integer key object ik, and the k value is simply just 39. Okay, so far so good? Right. And we just get another ik6, okay, which has the key value 6. Okay, I just wouldn't draw it. The more important things about these two objects. We'll get there. Now, let's do some basic assertions. If I say assert true, okay, first of all, I say ik39.1, the hash code equals 6. Should that be true? Yep, good, because 39 is over here. Good. Similarly, if I say ik39.2, and also it's talking about this value over here, that should also be 6. That's also fine. What about the next, this one here, also ik6 will also be 6. Fine, so far. And you wouldn't be so surprised if you simply say ik39.1 over here has the same hash code as ik39.2. It's hash code. Would be the same, right? Just say equal. They're both 6. Okay? Now, here's a critical thing. Can you tell me, how about this one here? Hash code are the same. What about equals over here? Are they the same? Okay, first of all, which version are we going to call? Default version or the customized version? Customized version, right? Which is defined exactly over here. You can see over here, right? That's the equals method. And for the equals method, simply just compare the k value. In this case, the k value is exactly 39 for each one of them, so that's okay. Okay, good. And then, of course, you can do more assertion over here about the about others. Okay, just 39 versus 6. Okay, in that case, the hash code will still be the same. Agree? Because 39 modulus 11 is the same as 6 modulo 11. The same. Okay. So far, so good. Let me now pose a question to you. So now you pretty much know how things work, what you call hash code. Let me ask you the following question. I'll lead you through the answer, don't worry, but I would rather you think about it first. I would propose the following change. Let me go back to the integer key over here. I would like to just make a one-line change over here. Rather than saying return this.k equals other.k. I'm talking about line 12 over here. I would do the following. Rather than this, I would say this dot hash code equals other dot hash code. Is there a problem if I change to this alternative version of the equals? So rather than comparing the key value there, I'm comparing their hash code, basically. Do you see any problem over here? Yeah, just before you have a question, we got answer. If you got answer, I'll rather hold it a little bit. Yeah, okay, good. Okay, if you really have no clue, I will give you a little visual hints. Consider what's going to happen over here. Try to recall what I said about if I'm given a key, and once I calculate the hash code, I know it's a valid index into the array. But what about the bucket that's stored in that particular index has multiple entries over there? What would be the consequence if I got a new version of line 12 over there? What would that be problematic? Okay, I heard yes. Okay, can anybody tell me what the problem is? Let's just use this example over here. Okay, let's say I'm trying to search for example, let's say I'm searching for, let's say I got a map over here, m.get 25. Also, I will have m.get, let's say 3 over here. Okay, you can use these two examples. Okay, anybody want to tell me what's going to be problematic here? Go ahead. Yeah, exactly, right. Okay, let me elaborate that a little bit, okay? That's exactly correct. What's wrong with this is, first of all, let's say I got the key for 25. I also got a key, let me say this. I got a key for 25, I got a key for 3. They do have the same hash code, agree? 25 modulo 11, 3. 3 modulo 11, also 3. That means they are both stored in this particular 3, index 3. As I said before, in order for you to find out the corresponding entry for 25, which is here, you have to somehow compare to see which keys is equal to this particular key, right? To 25, which is this one here. That's how we can distinguish between the elements over here. On the other hand, when we calculate the hash code for 3 here, that's also going to go to the same position. In that case, we must be able to distinguish it as well to say it should be this entry instead. Yeah, you got to search through the buckets. And when you search through the bucket, okay, how about this? Let me just write some conceptual code for you. When I already know I should go to this particular bucket, okay? What about, I'll just say it's B, okay, for bucket, okay? Basically, I would say for each entry in bucket B, okay? What I should do is, if the entry I'm looking at dot key dot equals over here, and then I will put let's say 25. Let me just say 25 over here. In that case, that means I found the entry myself, right? In that case, I can simply say return this particular entry. Okay, that's kind of the code I can write. So now the critical thing is to look at how the equals method is going to be used, the equals. Okay? So now, as we said before, in this new version of the equals method over here, we are simply comparing to see if the hash code are the same, right? So now when I try to search for 25, and when I try to search for 3, I'm basically trying to search the same thing, right? Because 25 and 3 got the same hash code. So I will get confusion. I can always just find the entry in just the first one, because the first one always match the hash code. So that's a problem. The problem is, with this kind of equals method here, to say hash code equals other than hash code, I can easily run into confusion, ambiguity. I will always find that the first entry there always has the same hash code as the one I want to find out. Okay? So for example, if I really want to find out the entry for, let's say 14, in this case, I wouldn't even get there because the first entry with 25 as the key already got the same hash code. So I would just ended up returning that entry. So that's a problem. Okay? It's a little bit subtle, but I would like you to know. So to recap, we cannot simply implement the equals method in terms of the hash code. That's the reason. Okay? That's something you cannot do. Okay, any question about this? That's the first example to do. Okay. Are we okay for this? Okay, very good. If we are good, let's go to another one over there. Okay, let's assume we do have this correct version of the hash code. Let's see how we can make some practical use of the hash code. So there is a data structure called hash table. Okay, maybe you have seen some brief usage of hash table back in 1022. We'll talk more about hash table a little bit later, but think about hash table just like a map. You got key and you got value. Every time you want to put an entry into the hash table, you put a key and a value together into it. Okay? So now let's see how we can use it, okay, quickly. So now let's say we got a hash table over here, and always you put the type of the key first. In this case, it's just an integer key that we just defined in the previous page. And also let's say we just get a hash table where each entry has a string value, integer key and string value. Okay? And then if you simply say new hash table, that means empty hash map to begin, hash table to begin with. Let's now create K1 and K2 being the two keys. Apparently you can see 39 and 39. Let me just draw again. So K1 over here is pointing to a new integer key objects with the key value 39. And over here K2 is just pointing to a separate integer key objects over here with also the key value 39. Okay? So now let's have a look at this. Assert true, K1 dot equals K2. True? False? True, right? Because if you just say this dot K equals other dot K, that will be fine. So this is completely okay. What about the hash code over here? That's also true. Yes, that's also fine. Okay? It's really critical that you actually got these two consistent. Okay? Now, if I want to put an entry into the hash table, let's see what's going to happen. You can see when I put a new entry into the hash table, I got to give a key. In this case, I give key K1. And then what's the associated value D? Okay, like that. Now, when I try to retrieve this entry back, I'm passing K2. Okay? So if I pass K2, so what does that mean? Well, even though K1 and K2 are different objects, right? But now how's the process going to go? Because since we already, well, let me tell you exactly how the process is going to go. It goes like this. First of all, given the key value we are looking for, so basically we just call internally, what's the value for K2 that hash code? Right? That's something we have already defined. In this case, it will simply be the K value for K2, which is 39, modulo 11. So that would be basically just 6. That means we'll go to the bucket at index 6. And once we go to the bucket, there might be multiple entries over there, right? There might be. How do we search them? We use the equals method over here to find out exactly which one has the associated value for K, 39. That's how things work. So notice one thing, even though we use K1 to put this entry into the map, but when we use K2 to actually retrieve it from the map, that's okay. We can still get a right value, D, over here. Because we have implemented the equals method and also the hash code method properly. Let me recap once more. It is really crucial to make sure the equals method and the hash code method, or equals and hash code, they are both defined properly. It's really important, okay? Because they're used in the same search process in different stages. The hash code is first of all used to calculate what's the valid index to go into the bucket, right? That's first step number 1. And step number 2, once we go into that particular bucket, how do we find out the right entry if there are multiple entries in the bucket? Well, we use the equals method to see entry one by one. So both methods are important. Okay? Question?
To go one by one with the bucket, we do a for loop. And we didn't do a for loop here. And the reason it's giving us the answer is because you added K1 right before doing that search.
Yeah, so basically, when we talk about for loop, it's only just for you to visualize what's going to happen. So once you get to 2011, you will see exactly how to implement the bucket. But conceptually, think about you might have multiple entries in that particular bucket. So the hash table over here is a library class in Java. They will have an efficient way to search through the bucket.
So if right after like table that put K1
Yeah.
key, if you put another line,
Yeah.
add another key.
Yep,
and
I see what you
I
mean.
mean, if you make sure the K1 is not the very
Yep.
last one that works.
It's a good question. How about I do the following addition? I see exactly what your question is. So now what about we do the following? Can I just add after K2 over here? I will just add a new key. Okay, I will say integer key K3. Okay, it's assigned to new integer key. What about simply just 50? The reason I choose 50 because if you say 50 modulo 11, it will give you the same value, 6, right? Also, the hash code for this will just be 6. So that means this, and then I'll try the following. And then after table.put K1D, I will do the following. I would say table.put. I would say K3 over here, and then let's say put E. Okay? So that means conceptually you can think about somewhere at index 6 over here, we actually got 2 entries over there, right? So we got, first of all, we have K1 and then D. Also, we got K3 and then E, right? But they have the same hash code, which is 6. So now let's say we do go to the bucket at index 6. How do we search through it? Conceptually, you'll simply just search through one by one. But how do I know if this is the entry I'm looking for? I use the equals method for the integer key. So that's why the equals method is very crucial. And for the same search, if you implement it wrongly, like what I suggested before, using just a hash code, you're going to get ambiguity. You always return just the first entry you see because they got the same hash code.
Very last question. Even if you make them like flip them like K3.
Doesn't matter. Yeah, as long as those entries are unique, then you're fine. Yeah, okay. Got questions? Oh, yes.
Go back to the slide.
Of course. Slides or here? iPad?
So the other slide.
This one or? You mean this one or next one? Here. Yes.
So like from the end of that code.
Yes.
The comma 39. So like before that, when you initialize the K1, K2, so in this bucket, you both have K39 and another K2 in that bucket.
Oh, no. Okay, let's say this. So the only 2 assertions I have is table.put K1 and D, and also table.put K3E, right? Okay, let me just redraw the bucket array very quickly, okay? So basically thinking this way. Let me put the bucket over here. So we know that first of all, when I put this K1, K1 has the integer value 39. So that means it should be at index 6, right? You think about this as it's a bucket conceptually, okay? So I will put K1, which is 39, and then followed by D. That's the first entry. That's just K1, just the integer value. Okay? And then when I put this guy here, K3, I know K3 is 50, right? So I'll put 50 here, and then followed by E. So now you can see once more, these 2 integer keys are somehow got different integer values. So they are not equal. So let me just say one more thing before you ask your question. Let me say one more thing. It is really important to see that over here you can see K1 over here with 39. If you say dot equals, you have K3. And K3 has the value 50. Would that be true or false? Just say equals. Well, it's going to be depending on the integer value, right? So that would be false. Okay? On the other hand, if you say K1 dot hash code equals K3 dot hash code, that would be true, exactly. This one being true, that means they are in the same bucket. This one being false means we can distinguish between them within the same bucket. Sure.
Take out the table put for the D, and then I rather put table put K1 and table put K2. Wait, actually.
Oh, okay. It wouldn't affect anything. So let me just make sure if I understand your question correctly. You're saying that rather than putting K1 here, you put K2?
No,
Or you want to put another line which will put K2? Okay, good question. So the question was, let's say after, can we say, okay, now let's say we have this. After this, I want to have just an additional line. I'll put it here, okay? If I have table dot put, doesn't matter K1 or K2, let me put K2, okay? If you say K2 over here, and let's say whatever, let's say E, okay? This is the behavior in Java hash table. What they will do is, they will actually, okay, let me just write it out over here. Let me tell you the procedure. First of all, we know K2 has the value 39, right? And 39's hash code is 6. So that means we go to this particular bucket over here, and then we realize it is this entry we are talking about, right? And then when we put E, what does that mean? That simply means we're going to replace the D over here by E. That's what they will do. Yes, because we are talking about the same key, right? So once we find out the corresponding entry for that particular key, I will simply override the value that's old with a new value. That's what you would do.
What would happen to K1?
Doesn't matter. If you say K1 over here, the same. Because remember, K1 and K2, they are equal. Right? So it doesn't matter if you put K1 and K2 here. I'll try to show you guys maybe some more hash table code later. But here, the main point for you to understand is, whenever you say put over here, you simply just convert K1, the hash code, into some index, and then go into the bucket array. And then when you want to get, that means you convert into hash code and search through the bucket using the equals method. Okay? Questions?
So that's possible that you do the get method before you're doing even a put method, right? Because you never put K2.
Oh, okay. Good question. The question was, let's say if I do the following. Let me use a different color here. Let's say even before, let me just say line over here, okay? Let's say even before I put table.put and then K1, let's say even before that. Let's say the bucket array is completely just empty, okay? If I already say get, table.get K1, okay? Basically, you're searching for something that doesn't exist. It's a little bit like a birthday book. If on the birthday book I say, now give me the birthday for Jim, but Jim has not been added just yet, it will simply return null.
But that's what you did on the last line. Because table that gets K2, but you never put K2 there. On the last line, you're getting K2.
No, again, understand that. That's true. When I put in first, I say K1, right? When I retrieve, I say K2. True. But remember, K1 and K2 are exactly have the same value over here. So as far as the keys are concerned, they are simply just equal. Okay, it's good that you pointed out. Okay, let me say that again. It was deliberate. K1 and K2, true, they are different objects, true. But since their K values are the same, so as far as the equals method is concerned, K1 and K2 are considered as equal. Okay, so that's why when I put in using K1, it's as if I put in using K2. When I try to search using K2, it's as if I try to search using K1, the same. Okay, so now one more remark. Whenever you override, make sure you override both the hash code and also equals. I'll show you the consequence if you did not override. Okay, I'll get there. Guys, any more questions? Okay. It is important to understand this, so I don't mind. We get a little bit slow. That's no problem. Okay. Okay, what I would do is, before I show you the last example, I would just like to go over quickly. There's some guiding principle for designing your hash code, okay? Basically, if I give you a hash code, of course, you don't have to redesign the hash code formula yourself. But if I give you a formula, you have to somehow justify to see if the formula is good or not, okay? So you don't have to come up with a solution. But if I give you some possible solution, you should tell me if the solution is appropriate or not, okay? There's some guiding principle. Okay, I'll show you basically over here. Okay, everything I've said, okay. This is the only principle you have to know about hash code. That's the only one, okay? So what does that mean? That means if I know that K1 and K2 are considered as the same key, let's say 39, okay? So what does that mean? That implies the hash code for these two equal keys must be the same, okay? So let's say 39 and 39. Since they are the same keys, their hash code must be the same. If you ever violate this principle over here, then it's not a good hash code. That's the only principle. Okay? And before I get there, I would like to just add one more page on my iPad and I will show it to you. So this only was slight logic you have to understand. Okay? For those of you, well, I'll try to give you one example. I'm not supposed to teach you too much logic to bore you, right? We know that if I say if P is true, that implies Q is true. Okay? That's pretty much like the formats over here. If K1 and K2 are equal, then that means the hash code are equal, right? Equivalently, for those of you who took 1019, there is something called contrapositive. If that rings any bell for those of you who took it. If it doesn't, that's fine. I will put it here. That means equivalent to saying not Q implies not P. Okay, let me use one example to show you. Very cliched example. What about P? It rains. Okay, what about Q? I use umbrella. If I know how to spell that, whatever. Okay, I forgot. Anyway. Okay, if it rains, then that means I use umbrella. Okay, did I spell wrong? Okay, pretend it's umbrella. Okay, yeah. Yeah, sorry, I haven't used that word for a long time in writing. Okay, so now if it rains, that means I use umbrella. But what about if I didn't use umbrella? If I don't use umbrella, what does that mean? That means it doesn't rain. Okay. So these two are logically equivalent. Okay. If you're interested in proving these two being equivalent, drop by my office hour, I'll show you. But for now, you can just take it for granted. When I say P implies Q, it's equivalent to saying not Q implies not P. Okay, how is this useful? We can get a slightly different insight into this principle here by rewriting it to its equivalent form. So over here, I say that if K1 and K2 are the same, are equal keys, then that means their hash code must be the same. How do I apply contrapositive here? David, go ahead.
If their hash codes are different, then they have to have different keys.
Exactly. If the hash code are different, then that means their key must be different. Okay, that's just contrapositive. Okay, that's the only thing I want to mention. So you don't really have to memorize this principle here. I think if you really understand what hashing is doing, as long as you make sure equal keys have the same key, so have the same hash value, that's it. Okay. I do have some cases for you to consider. Yes, question before I move on. Go ahead.
Is that basically like saying if the keys are the same, it implies that they're in the same bucket, and if they're not in the same bucket, then the keys.
There's another way to look at it. Very good. Good. So let's look at the previous one. I like that. How about another way to see this is, actually I really added to my slides. That's a good interpretation. So basically this formula is saying if the keys are equal, they must be in the same bucket, right? Because the same bucket means the same hash code. Now, if the two keys are in different buckets, they better be different, right? Otherwise you miss the search. Good. Now, some special cases for you to consider. Can you imagine what's going to be the possibility if I tell you that today if I have two different keys, if the two keys are different, do their hash codes necessarily have to be different or the same? If the two keys are different. Well, let's use, David, go ahead.
You showed us examples where
Yeah,
the keys are different.
exactly. Yeah, exactly. What about we review those examples quickly? Okay, basically the reason I'm mentioning this is don't get confused with the guiding principle. The guiding principle over there must be true always above. So here I'm just talking about some special cases. You gotta do some case analysis. If the keys are different, for example, their hash code might be the same, in which case, for example, 25 modulo 11, you will get 3. 3 modulo 11 also get 3. They're different keys, but they got the same hash code, collision, okay? On the other hand, their hash code might be different, which is natural. For example, 25 and 1, they just belong to different buckets, right? What about next one? If I say the two hash codes are the same, do these two keys must be necessarily have to be the same or different? Or can be either one is possible? Can be, that's okay. What would you say? we just woke up.
Keys could be different.
Yeah. Keys can be different, right? Yeah. Okay, or can be the same. Let's say this. If the hash code being the same, that means they're in the same bucket. Being in the same bucket, they don't have to be the same. Wow, actually what? Over here, if I say they are not the same, in which case, for example, you can see 25 and 3, hash code the same, but they are hash code the same, but they are not the same key. Okay. On the other hand, how about this case over here? If I say the two hash code being the same, and K1 and K2 are the same, what does that tell you? Well, basically, the same key object, exactly, the same key, right? It's basically telling that your hash code is okay. It doesn't recalculate different values for the same key. Okay, do review this slide over here. I'm just showing you different scenarios for you to consider. And don't get confused. I got one last code fragment to show you, one last one. And this one will be very useful. It shows you the consequence if you did not overwrite the hash code. I said you should always try to overwrite the hash code, but what if you didn't? Okay, again, let me switch to iPad over here. Let's see how that code is going to look like. Okay, let's look at that together. So the change over here is, you can see that over here, we still get integer key class over here. And then what we get is, we still got the overridden version for the equals method, the same. We're just comparing the key value. But now, we don't explicitly redefine the hash code anymore. Default version. I want to show you just one thing in Eclipse very quickly so you will get an intuition. If I go back to Eclipse over here, and then, okay, let me just, I'll make the source code available as usual to you after class. So what I will do is, I want to show you this particular test over here, okay? So what I would do is, have a look at the integer key class over here. You can see that we got the integer attributes, and also we got a constructor. No overriding of the hash code, which means we're going to use the default version from the object class. Okay, let's see exactly what's going to be produced. If I go back to the tester over here, okay, the test. Let's say this. What I want to show you is, let me see which one I want to show you. The hash code. Okay, let me put, what I can do is, I can do some expression check. Okay, let me just put the breakpoints over here. Okay, I'll put the breakpoint at line 15. That's what I will put. Okay, so notice one thing. I got 39, 1, and 39, 2. They have the same key values, but they're different objects. Now the question is, would their hash code be the same? According to this version over here. We thought they should be the same, but they wouldn't be, because we did not override the hash code method. Okay, let's double check. That's what I want to show you. What you can do is, you can just say, run the debugger over here. And then, we stop here. Okay, if you haven't tried yet, there's something very cool called expressions over here. Okay, if you wonder how you can find it, you can just go to Window, Show View, and you will see expression somewhere. Okay, in this menu here. Okay, I'll leave that to you. So what I can do is, I can just put an expression here. First one, I would say IK39 underscore 1, that's the first object name, dot hash code. In that case, I got a number here, 204A425748. It's an integer. It's based on the address for this particular object. Okay, but the value itself is not important. What I would do is, I'll do the second one. I would say IK39 underscore 2 dot hash code. And then I'll say OK here. Okay, that one there is a different number, as you can see, right? One of them is starting with 20, the other one starts with 18. Basically, I want to show they are different hash code. All right? If they are different hash code, what does that mean? According to your interpretation, if they are different hash code, they're in different bucket. All right? Keep that in mind. I really like that interpretation. Okay? If they are in different hash code, that means these two, even though they are both 39, but they are in different buckets. Okay? Let's now go back to the source code over here and see what's going on. Okay, what I want to show you is this. Again, we got IK39, 1, IK39, 2. They are different objects, but 39 and 39. Okay? So now let's try the hash table that we did before. I created K1 and K2 being both 39. And now if I say assert true, K1 that equals K2, that should pass. Agree? Both 39. So now when I say assert true, their hash code are different. Also true, right? I just illustrated to you. So now here comes the interesting bit. If I say the following, if I say table.put K1 and D, okay, we put it in some bucket. How about that? Just some bucket somewhere. And when I try to say table.get K2, so now notice one thing. Oh, that's TED Talk. I don't want to watch that now. Okay, so now K1 here and K2 over here. We know that K1, oh, sorry, I don't need to write it again. We know from the previous line over here, K1, the hash code, is not the same as K2, the hash code. That simply means conceptually, the D here is stored in a bucket that is going to be different corresponding from K2. Agree? So that is why when you say K1 and K2 here, we will simply get null. It doesn't exist. That's kind of the weird behavior. As opposed to what we saw before, when you try to put in using K1 and you want to retrieve using K2, you will get exactly what you expected. So that's the difference, right? So the difference is, in this correct version over here, we properly redefine the hash code. But in the wrong version, we did not use it. We simply use the default version, which only generate hash code for each distinct objects. Okay? Okay, guys, any question about this? Are we okay? That'll be the last example for hash code. Okay, good. If you're okay with it, okay, let's go on a little bit more. I promise I would finish 10 minutes earlier today because I do have a midterm survey for you to fill in. I send you a Moodle announcement. So you can take your time writing it and make some suggestion to the course. Okay? But I would only spend about 10 minutes doing some new topic, and then we'll be done. So this topic here, asymptotic analysis of algorithms, the most part of it is mainly just math. So we're going to do a little bit of math, reviewing what you learned basically back in the high school, some functions. But the usefulness of this lecture here is we're somehow going to say, given a piece of Java code, you want to judge to see whether the code itself is efficient or not. So we talk about efficiency over here, right? We got some intuition from the hashing function, but now we're going to talk about it more formally. Okay, let's see. Okay, so now let's first of all talk about, since the title over here, just to give you an overview. So whenever we talk about asymptotic, that means towards the limits. We are talking about very large inputs for the program. And when we say algorithms, I will explain that in just a moment. So this just introduce some terminology. So we talk about algorithm and we talk about data structure. We don't really cover so many data structure and algorithm in this course, only very simple ones, maybe some sorting algorithm later. But in 2011, that's exactly the topic that I cover. But let's just bring everybody to the same page. What is a data structure? The only two data structure you have learned so far and programmed by yourself, one-dimensional array and two-dimensional array. So these are the only two. Okay, so they are data structure. Data structure is a systematic way to organize your data. For example, one-dimensional array, you got 0 until count minus 1. And also two-dimensional array, you got row and index, row and column. Okay. Okay, so now for using array, as you learned from the birthday book tutorial, if you want to add things into the array, it's very easy, just add to the end. But if you want to delete certain slot from the array, it's going to be challenging because you may have to shift everything to the left by 1. So that's going to be costly. So the point is, you may have to make a decision which data structure to choose. That's more for 2011. Okay, what about computational problem? Basically, just a problem for you to solve. Like the birthday book problem, that's a problem for you to solve. And the way we specify problem is we give you an input. Let's say we just give you a sequence or an array of numbers. And then we will tell you what the expected output is. Let's say we simply want to do a sorting. Okay? So what does it really mean to sort? Let me just illustrate that to you very quickly. Okay, let's say this. If I tell you that, if I give you, this is how you do a sorting. Let's say I give you 3, 1, 2, and 4. So that's the input. Okay, now I say I want to sort it in a non-descending order. So what I will do is, I will tell you what the output should be. The output should be such that all the elements should still be in the output array, but it's going to be arranged so that at index 0 is going to be smaller than or equal to the element index 1, and etc. So what you will get is something like 1, 2, 3, 4. Okay? But how exactly you go from input to output, that's up to you as a programmer. So we'll show you some naive strategy for sorting, namely selection sort and insertion sort after the reading week. We'll do that. It will give you more insight into the sorting, but it's a computational problem. Okay, and let's see, what about algorithm? Algorithm will be what you are going to learn in 3101 later in the 3rd year. Okay, so algorithm is simply a solution to the problem you have. So now, by the end of your graduation, you will learn about at least 5 or 6 different ways of sorting. Insertion sort, selection sort, we're going to cover in this course. Maybe merge sort, quick sort, 2011. Merge sort, quick sort, heap sort as well. Many other sorting algorithms that you will learn. But for you as a programmer, you're going to judge which one to use. Okay. Okay, so far so good. Just terminology. Just read it through. Make sure you're familiar with them. Okay, so now let's get some concepts straight. How do you measure if the solution you present is a good one? Okay, let's have some criteria over here. Number 1 criteria is got to be correct. If it is not correct, but it's very fast, it doesn't matter. I can tell you what's the fastest solution to every problem. I can just print hello world. That's the fastest. Okay, so correctness is number 1. No question about it. But for this course, we want to go a little bit beyond this, efficiency. Okay, but when we talk about efficiency, let's be more precise. There are 2 things we can worry about. One is about time complexity, like how long exactly will your algorithm run, and otherwise space, how much space you will take. To your intuition, which one is more critical? I heard time. Okay. Well, in today's technology, of course, we got lots of space for your hard drive or memory. At the same time, the machine speed is also very fast. I would say still, because sometimes you may have deal with maybe millions or even millions of size of inputs. In that case, time is actually more important. Space is not the thing. You can just always buy external drive. But for time is really important. But we'll talk about this. But for now, let's just get convinced time is actually more important. Okay, correctness is always priority, and then we'll get time. I will show you one example where the way you write your program is going to affect a lot about the time. I'll just use that example. Okay, so basically I'm just saying over here, so there are 2 main factors for the time for your program to run. One is about the size. For example, if you want to search through the bucket array or search through the 1-dimensional array for a particular elements, search through a 10-element array versus searching through a million element array is different, right? And also, let's say if you want to do some sorting on the array, if the array is completely out of order, it will take more work. If the array is already sorted, nothing to do, right? So that's basically my point. So now, how do you determine the running time of your solution or your Java methods? Well, there are 2 ways. We'll only cover way number 1 today. Okay? Way number 2, which is something you have to know for the rest of the course. What about approach 1? Approach 1 is very similar to what you did in high school. In high school, if you want to know about something in chemistry, what do? Go to the lab and run it. Okay? Basically, approach 1, just do some experiments with some inputs. But number 2 is really something we're going to cover carefully, maybe after the reading week. But let's just see approach number 1 and criticize it, and then we are done, okay, for today. Okay, so now let's say, so we're going to implement this in Java, and then we're going to run some inputs. Let me give you this particular, and then for each test, we're going to see exactly how much time is going to elapse, okay? Let me give you this particular program over here. Basically, there's a layout. In Java, there's a system class. You can just get what's the current time in milliseconds. And we simply say what's the start time as a long number, and then as we run the method there, as soon as it is terminated, we just record what's the ending time and subtract one from the other, so we know exactly how long the method has run. Okay, now let's see the following. Okay, so of course once we're done, we got to do some statistics, some visualization, but let's just see this program here. So this is a problem. Okay, basically the input is it's going to be a character and then some integer. The output is very simple. Repeat the character for exactly that many times. So if I give you input star and then 15, repeat star for 15 times and put, let's say, print it to the console or write it to a file. Doesn't matter. Okay, I'll give you two alternative versions. Version number one, I initialize a string over here, empty, and then each time I simply use a plus equal, the character, right? For 15, I just run a loop. The second one is similar. Also, I need a loop to see exactly how many times I got to repeat, but now I'm using a library class called string builder. Okay, I simply call sb.stringbuilder.append the character. Okay, let me tell you exactly the difference is, and tell me your intuition, which one's going to be faster. When I say, for example, first of all, when I say s plus equal a character c, so this, we know that it's equivalent to s is assigned to s plus c, right? That's approach number one. What at the runtime, right-hand side is going to be created for a separate object, s plus c. Let's say, for example, if I say, if s is currently pointing to, for example, Alan, okay? I say s plus, s is assigned to s plus, let's say, character c. So how do I do that? First of all, I have the duplicated string somewhere, Alan, put c at the end. Afterwards, reassign s into here. You can see this maybe some waste of memory, right, in the intermediate states. That's approach number one. For approach number two, if I have string builder, it's simply just an object, string builder. And then somehow under the hood, it maintains maybe an array of characters. Okay, maybe already A, L, A, N. Now, if I say string builder dot append, maybe some character C. So what would it do? You wouldn't create any intermediate objects. You would simply put C at the end. That's it. Hopefully you get an intuition, right? Which one's faster? Second one, right? Let's see how faster it is. Okay, just show you the points. Okay, let's say approach number one with naive plus equal. So solution number two is the append. When we got 50,000 times to repeat, even though one is not too bad, right, for the solution number one, right? It's not still just a millisecond, right? How about this? Okay, we increase the input size by 2 times, and then it's only about 3 times roughly, and this remains to be the same. Okay, let me tell you what the conclusion is. As you get to the very large input exactly over here, 12 million times, it takes about 3 days for the first solution. And the second one, 135 milliseconds, okay? Well, you can try it, the first one, and let me know if that's really 3 days. Well, you got a whole reading rig, right? Let me know, yeah. It might take longer if your machine is old. Anyway, okay. Basically, I'm just trying to show a typical experiment. You try different methods there, implement them, and then try to run them and see exactly how long it's going to take, okay? So now, can you see, when you see a graph, I want you to notice one thing. Give me 2 minutes, I'll finish, okay? One thing is, you can see the way the function grows, they are both linear function. This is something I will touch upon after reading week. Let's have a very quick criticism for this kind of experimental approach. What's the drawback for this? Well, basically you can see to do this experiment here, I got to implement approach number 1, I got to implement approach number 2, and then run them. What's the drawback here?
If I wanted to see how long it took first, I would have to wait 3 days.
That's true. That means I really got to run it on the machine, right? Okay. And also I really make sure I finish the Java implementation and compiles before I can run it, right? And also when I run the 2 algorithms, are they really run on the same machine, the same CPU, the same OS? and the same process load. That's really the physical constraint you've got to consider. Okay? That's exactly what I wanted to say here. Over here, basically, these are the constraints that's really not so good for the first approach. What we really want is we want to do some paper analysis. So that will be the focus for after the reading week. Okay? Let me stop here.